Hey, this is Math 7, Unit 8, Lesson 18, comparing populations using samples. Alright, so in the first activity, it's called same mean, same MAD, mean absolute deviation. So, okay, let's take a look at this. Without calculating, tell whether each pair of data sets have the same mean and whether they're the same mean absolute deviation. Okay, so just looking at set 1, or set A and B, we're looking at kind of breaking it down apart like this. Here we have numbers from 1 to 14. I would say that the mean here is somewhere probably around 6 or so, 6 or 7, right? So that's probably the mean is somewhere about there. Over here we have numbers from 7 to 21 to 34. That mean is going to be somewhere, closer to 26 or so, something like that. Are those means the same? We would say here the means are different, that's for sure. But in terms of the mean absolute deviation, that is, how far away are the numbers on average away from the mean, well, here I have, if I put 6 there, I have a range of 1 to 14, which means I'm talking about 13 number difference, and this middle one's somewhere in the middle, not too bad. 21 to 34, that range is also about 13, so if this one's in the middle, again, not too bad. I would say that they have a mean absolute deviation that is very much the same, or very similar at least, because again, how far it deviates from the mean for each value is very similar. Okay, for x and y, okay, the mean for this one, 1 to 5, is going to be right in the middle at 3. For y, the mean is 1 to 6, so the mean is going to be here in the middle at actually 3.5. So is that different? It's different, but yet it's very much, very, very similar. Okay, so we could say it's a different mean, that's for sure. It's a different mean, very close. So up to you if you want to do that one. I would say means are different here. Now in terms of the mean absolute deviation, those are going to be different as well. Okay, I mean, really, yeah, they're going to be different as well, because this one's going to be a different average away from the middle. That one is because this has a range of 6, this has a range of 5, so they're going to be stretched a little bit more. Is it significant? Probably not, but it is different. Over here we have a 47 to 62. That means going to be somewhere right in the middle here. If we had to take a guess, so somewhere in the mid-50s. Over here we're 37 to 72, so that means going to be right about the mid-50s. So we'd probably say, let's go back here. I'm going to say this one was the same based upon what I'm doing right here. I'll say these means are about the same. They're close. If I'm going to say these means are same, mid-50s, then I should say that's the same too. But here, for your mean absolute deviation, going from 47 to 62 compared to 37 to 72, those are definitely going to be different. It's going to be a lot further away to get to 37 than it is to get to 47. So you'll have a major difference there in your mean absolute deviation. Okay? Now the reason that's important is that, again, that mean absolute deviation, what you're talking about is if I got lots of data samples of data, and I talked about their means, would the means be close to the population mean or not? And the greater that difference, the greater the variance, the more likely it's going to be further away, right? So this would not be a good data set that's representative of the population because the mean absolute deviation is too great. Okay, whereas this one is going to be a lot better, at least compared to these two. It just happens to be a little better number. Anyways, let's move on. With a heavy load, consider the question: do 10th grade students' backpacks generally weigh more than 7th grade students' backpacks? Here are the dot plots showing the weights of backpacks for a random sample of students from these two grades, 7th grade and 10th grade. Okay. Now just looking at this, we have a lot of dots right here, and then some right there. Over here we have a bunch right here, and then some right there. So the 7th grade backpacks in this sample weigh more than a 10th grade backpack. Okay, it says, did any? Well, the 7th grade backpacks right here, these three for example, those three right there, all weighed more than that one right there. So yes, they did, right? So 3 backpacks weighed more than the lightest 10th grade backpack, right? So those 3 weighed more than the lightest one. So just ask the any. The mean weight of the sample of 7th grade backpacks is 6.3 pounds of 7th grade. Do you think the mean weight of the backpacks for all 7th grade students is exactly 6.3? So this is just one sample. And in the sample they said, well, the mean weight of the sample is 6.3. Okay, so somewhere right about there. So the question is, if I did this again, would I get the same mean weight? If I did the same sampling again, a random sample of kids, do I think I'd still end up with 6.3 on the next time I did it? Well, based upon what I see here, I would probably go with no. The reason I say no is there's a lot more that are less than that, and that 6.3 value for this sample is probably has a lot more to do with the fact that I picked 3 heavier backpacks. Okay, so for my answer here, I would say no, because this is just one sample. Again, the more samples you do, the more accurate your mean is going to become. Okay, so we would say that the population, because we're talking about all, we'll say the population will be a little different. How much different? I don't know, but we'd have to do it many times to get a better sample mean for the entire population. Now the mean weight of the sample of 10th grade backpacks is 14.8 pounds. Do you think there's a meaningful difference between the weight of all 7th grade and 10th grade backpacks? Okay, is there a meaningful difference between the weights? And what we'd say here is we would say yes. Now the reason we'd say there's a meaningful difference between the 2 weights is the reason there's a meaningful difference is that when you look at it, there's very little overlap of data. And what that means is when you come back over here, that overlap is what you're looking at. How many sample pieces cross over, right? This is our only overlap. It's right in this range right here, there, right? That's our overlap between the 2 things. If you don't have a lot of overlap, what that means is that you really have 2 different sample spaces, and your means are going to be very different, right? I have this group over here, I have this group over here. Besides those 3 data points there that are on the outside over there, there's not a lot of overlap. So when there's not a lot of overlap, that means that there's a meaningful difference between the weights of the 7th and 8th grade. Generally speaking, we would say 7th grade backpacks are lighter than the 10th grade backpacks. Okay, and you can see it based upon the data that you saw. Okay, if there's not a lot of overlap, we would say it's not meaningful. I'm sorry, if there is a lot of overlap, then we would say it's not meaningfully different. They're too close together. Here are 10 more random samples of 7th grade students' backpack weights. Okay, so more backpack weights randomly there. Samples 1 through 10. And you can see they're plotted out here. And then over here we find the mean weight for each sample. So the mean weight of the first one is 5.8. So the mean weight sample is going to be here. I'll use a different color here just to kind of mark this. So you have a sample of 5.8. This one over here is 9.2. This one's a 5.5. Then we have 7.3, 7.2, 6.6, 5.2, 5.2, 6.3, and 6.4. Okay, so just kind of as a kind of note where that's at, take a look here. I'm going to draw a little zigzag just for fun. This is where our data points are. They go there, they go out there, out there, out there, here. And the zigzag doesn't mean much, but if you take a look at that over time, you kind of say, well, where about is that data at? You know, and kind of drew a little line through all that. You probably would say, well, the data seems to be lining up somewhere down this range right about here, right? So most of the data is there. Oh, that's a curvy line. About 6.5 to 7, somewhere. I curved from 7. That's okay. That doesn't matter. It's not part of the question. But just looking at the means, we go, huh, the overall mean should be with this data point somewhere around there. Well, let's see what they're asking us to do. Question 1 says, which sample has the highest mean weight? Well, the highest mean weight was over here, sample 2 with 9.2. That's our high. That's our highest weight right there. Which sample has the lowest mean weight? Well, lowest mean weight in this case here, there's actually 2. I'm not sure my answer book teacher book only showed 1, but maybe they changed it later. These are our lows over here at 5.2. What is the difference between these two sample means? Okay, so we had 9.2 and we had 5.2. So the difference in the sample means is going to be doing 9.2 minus 5.2 for 4. So 4 is the difference of means. The difference in means is 4. Now all the sample means have a mean absolute deviation of about 2.8 pounds. That's our MAD. So our mean absolute deviation for all the samples is about 2.8. Express the difference between these two sample means. So express the difference between the two sample means. So express the 4 as a multiple of the MAD. Okay, we want to express the 4 as a multiple of the 2.8, meaning this. We want to do 4 is a multiple of the MAD times some other number. Okay, so that's what they're asking. Can you express the difference between these two sample means? Okay, difference between these two sample means, that's one kind of phrase, that's the 4, as a multiple of the MAD. So, can we do that? Well, there it is right there, so what number should go right there is kind of the question. To figure that out, what you do is you would actually think of it like this. 4 equals 2.8, and we could say x. We're going to divide both sides by 2.8, and we come up with here is that x equals about 1.43. Let's just do it real quick on my calculator to confirm. So 4 divided by 2.8. Yep, and we can round that up to about 3, so 1.43. All right, and that's what we have. Now, are these samples very different? Explain and show your reasoning. For us, we would say, are these samples very different? Yeah, well, first of all, the answers are different, but are the samples different? The samples are from the same population. Okay. Yeah. So they're not very different. First of all, sorry, I had to think real quick. It's early. So they're not very different. And the other thing we see is that because of the mean absolute deviation, they are all within the mean absolute deviation of 2.8, meaning there's lots of overlap. Okay, think of it this way. Are all the samples are they close to that mean absolute deviation overlap? So if the mean absolute deviation is about 2.8 and this one here is at about 5.5, then I'm going to go out to this range here, 7.5 down to 3.5. Okay, so the sample there, those are in that area. Here about 9, going down to 7 to 11. I'm going to come out here to 3.5 to 7.5. I'm going to come out here to about 5 and a little 9. Go here 5 and 9. 4.5, 8.5. Just going out. Oh, I should be going out to 2.8. Sorry, I need about 3. Almost 3. Let's extend a little bit more. Extend a little bit more. A little bit more, about 3-ish. I was going out 2-ish. So go out a little bit further each time. So what I'm doing is I'm extending from the mean for each one about 2.8 out this way. Okay, just estimating, not perfect. So when you look at that picture there, is there a lot of overlap with our blue color? Do a lot of these values overlap each other? Yeah, they really do. Are there a lot of values that aren't in that overlap region? Well, yeah, there's like some right here, there's some over here. I do have little pockets here and there, but for the most part, most of the values are in that overlap region, aren't they? Okay, they're within the mean absolute deviation. There's a few that don't quite fit, but most of the data is in those overlap regions. So because of that, we would say they are not very different. So are they very different samples? Nope, they're not very different. Even though we had a difference of 4 between the highest and the lowest, overall, because of the mean absolute deviation, they're not that different. So remember, our sample of 10th grade students' backpacks had a mean weight of 14.8 pounds. The mean absolute deviation for the sample is 2.7. Okay, so going back to the 10th grade kids, they had a mean weight of 14.8, and the mean absolute deviation is 2.7. Your teacher's going to assign you one of the samples of 7th grade students' backpacks to use. So I'm just going to go ahead and use sample number 1. Okay, sample number 1. So what is the difference between the sample means for the 10th grade students' backpacks and the 7th grade students' backpacks? Well, we're looking for the difference between the sample means of the 10th and the 7th grade. Well, I'm using sample 1. Sample 1 had a mean of 5.8, so the 7th grader was 5.8. The 10th grader was 14.8. Okay, so 7th grade is 5.8, 10th grade is 14.8. So the difference is 14.8 minus 5.8. So my difference is 14.8 minus 5.8 is 9. Okay, so for part B, it says express the difference between these two samples of sample means, which was 9, right? That's a 9, as a multiple of the larger mean absolute deviation. Now, the mean absolute deviations we had to choose from was the 7th grade one, which was 2.8, or the 10th grade one, which was 2.7. So the larger of those was 2.8. So we're going to set 9 equal to 2.8, and we're going to multiply it by something we don't quite know yet. And then if I solve that there, I would do 9 divided by 2.8, and that gets me about 3.2. Okay? So the difference between these two sample means as a multiple of the larger of the MADs, which was 2.8 back from the 7th grade group, becomes 9 equals 2.8 times 3.2. Now, do you think there's a meaningful difference between the weights of all 7th grade and 10th grade students' backpacks? Explain or show your reasoning. Okay, so we're talking about being a difference between these two things. Okay, meaning if there's a difference, there's very little overlap. That's what we're talking about there. So from what we've seen, we would say yes, there is a meaningful difference, okay, which means to us that there is little overlap, right, in the data. They don't cross over there. Okay, now the reason we also say that is because the difference in means is more than 2. Okay, the difference in means is more than 2 mean absolute deviations. Okay, so there is a meaningful difference. Okay, now our difference in means here was what? It's more than 2? Yeah, it's 3.2, right? That's significant there. So the difference between those is more than 2. We had 3.2 as our difference there. That is far more than 2, isn't it? Okay, so generally speaking, if the mean absolute deviation, okay, is greater than 2, then we say it's then there's a meaningful difference. Okay, so kind of keep that in mind as we do the next activity here. Okay, all right, moving to the next one. Okay, when anthropologists find steel artifacts, they can test the amount of carbon in the steel to learn about the people that made the artifacts. Here are some box plots showing the percentage of carbon in samples of steel that were found in 2 different regions. Okay, this is the percentage of carbon in steel, we find it here. Was there, and this is a box plot, right? So that means that our median is here. Okay, that's our median. And then we have the range of values that go along there as well. Okay, so was there any steel found in region 1, this top one here, that had more carbon than some of the steel found in region 2? Well, region 2 went to right here, this point. So was there anything in this that was greater than what's over here? Yes. In fact, we would say yes, most of it, right? Most of it was. So most of the carbon in region 1 was greater than what was found in region 2. Was there any steel found in region 1 that had less carbon than some of the steel found in region 2? Again, we would say yes, and that's because the box plot extends into the region 2 box plot, right? So because all these values go into the same region as the region 2 values here, then yes, there is less carbon. There are some values that are less than what's found in region 2. Do you think there's a meaningful difference between all the steel artifacts found in regions 1 and 2? So to find that meaningful difference, we're looking at something a little bit different now. Now we're talking about, because we have a median, we have to decide, we're comparing those medians. Okay, so you can look at the medians, and the medians are very different, yes, but we also have to look about, the question really is, do we see much overlap, right? A meaningful difference means that there's not going to be much overlap, but do we see overlap? Yeah, there's some overlap happening, right? So because there's overlap happening, these values here, right, all these values here are in the same overlapping region. That's overlap. So because there's overlap, it's not a significant difference, okay? Or it's not significant. Okay, let's look at my notes, make sure I get this all clear for you guys, all right? So, so there's some overlap. Actually, I should say it like this. So there is some overlap, but the boxes, let's do but, the main boxes, which is most of the data, are far apart. So while there's some overlap though, we could say that our main values are not near each other. If those boxes overlap, we would say there's not a meaningful difference. But because most of the values are in those spaces there, okay, we would say that there is a meaningful difference. So let's go with yes. There is a meaningful difference. Okay. Number 3. Which sample has a distribution that is not approximately symmetric? So not very symmetric. Alright, so symmetric, if it's a box plot and it's symmetric, it should look something like this. Alright, meaning that the lines that come off it are about the same length. Okay, so the one that's not symmetric, or the least symmetric, we would say region 1 is the one that is not as symmetric because it has this long line that extends. That line makes it not symmetric. You have some very weird values way out to the left hand side. These values here, they're stretching it out, doesn't make it very symmetric. This one's a little more balanced. You can see the box, main box is in the middle. Here the box is way over there from where the data range is at. So what is the difference between the sample medians for these 2 regions? Okay, well, we need to estimate the sample medians here. Now the median for the first one is at this point, so about 0.64. The median for here is right about the middle, maybe 0.46. So I would do 0.64 minus 0.46. So the difference in those medians is about 0.18. Alright, so that's the difference between the two medians. Doing the 0.64 minus the 0.46 to get me 0.18. Express the difference between these two sample medians, that's one big chunk, which is 0.18, as a multiple of the larger interquartile range. Here's our interquartile range, so which one of these numbers is the larger one? The larger one is 0.05, so do 0.05 times some value, which we're going to find here in just a second. Okay, so we're going to express this number as a multiple of 0.05. So to find that value, we're going to do 0.18 divided by 0.05, and we end up with 3.6 right there. The anthropologists who conducted the study concluded that there was a meaningful difference between the steel from these regions. Do you agree? Well, what we said before is that if this value is greater than 2, it shows a meaningful difference. So we would say, yes, we agree, there is a meaningful difference. And that's shown there by having a 3.6 as a number that we find out there. So that tells you there's an issue. Okay, so let's summarize this long lesson. It says sometimes we want to compare two different populations. For example, is there a meaningful difference between the weights of pugs and beagles? Here are a histogram showing the weights of sample dogs from each of these breeds. Okay, the red triangle shows the mean weight of each sample. 6.9 for the pugs, there's the pugs, and 10.1 for the beagles. The red line shows the weights that are within one mean absolute deviation of the mean. So that's all within one mean absolute deviation. All those values there, and these values here. We can think of these as typical weights for the breed. These typical weights do not overlap, right? The lowest here is about 9.5. So again, this is one scale, they don't overlap. In fact, the distance between the means is 10.1 minus 6.9, or 3.2. So the distance from here to here is 3.2, right? Over 6 times the larger mean absolute deviation. Okay? That's a lot. So we can say there is a meaningful difference between the weights of pugs and beagles, right? They're just too far apart from each other. Okay? So, is there a meaningful difference here between the weights of male pugs and female pugs? So a different thing to look at. So here's a box plot showing the weights of sample of males and females. We can see the males are here, the females are here, but what do we also see? We see a lot of overlap, don't we? All this region here to here, all this is overlapping stuff. And the big thing here is that the two big boxes actually overlap as well. So there's a lot of data point that's going to have similar values there. So we can see the medians are different, but the weights between the first and third quartiles overlap. So these two weights are these two boxes. This is the first and third quartile. So a lot of overlap is the point. So we would say in this case, there is not a meaningful difference here. Where before, there is. There is a difference, there's a big gap there. Here, there's overlap, so no. So in general, if the measures of center for two samples are at least 2 measures of variability apart. If there are at least 2 measures of variability apart, right? So an MAD of 2 or interquartile range difference of 2, we say the difference in the measure of centers is meaningful. Visually, this means the range of typical values does not overlap, typically, okay? If they are closer, then we don't consider the difference to be too meaningful. So if it's overlapping, then the difference is not meaningful. If they're far apart, then the difference is meaningful. That's your idea with lots of numbers. Okay, I'm going to pause there, let you work on your homework. We'll come back and check that together in just a few minutes. Alright, here we go, homework for lesson 18. Lynn wants to know if students in elementary school generally spend more time playing outdoors than students in middle schools. She selects a random sample size 20 from each population of students and asks them how many hours they played outdoors last week. Suppose the mean absolute deviation for each of her samples is about 3 hours. Select all pairs of sample means for which Lynn could conclude there is a meaningful difference between the two populations. So again, you got to go back up here. Make sure you understand what a mean absolute deviation is. Her sample mean absolute deviation is about 3 hours. So it's thinking about kind of plus or minus every value with 3 hours. Just to say, what is the range that would fit within that sample population? So here she has 12, and she wants to say there is a meaningful difference. So that means we want to have no overlap or very little overlap. So think of this way. Elementary school is 12 hours. So if I do 12 hours here, and middle school is 10 hours, if I subtract 3, I'm at 9. Here, if I subtract 3 or add 3, I'm at 13. So you're thinking about it like this. Here's a number line. Here's the numbers 10. Here's the number 12. Okay, this is the sample for elementary, and I can go from 12 down to, well, let's go 9, 11, 13, 14, 15. Here's 9. So for the elementary guys, they can extend here down to there. For the middle school, it's 10, and we're going to go 1, 2, 3, down to 1, 2, this way. Okay, so is there overlap? There's a lot of overlap. So is there a meaningful difference if there's all that overlap? We would say no, there's not. So this is going to be a no one. Now, can you do that for each one of these? You could, but I just want to visually show you why this is not a correct solution. For number 14, if I subtract 3 from 14, I'm at 11. If I add 3 to 9, I'm at 12, which means 11 is going to be overlapping with 12, so there's overlap, no meaningful difference. Okay, I have 13 and 6. Now this one here, if I look at going from 6, 7, 8, 9, 10, 11, 12, 13, here's 13, here's 6. Okay, let's say I subtract 3, that's my MAD, 1, 2, 3, that's my lowest value for the elementary school. For the middle school, I'm at 6, if I go up 3, 1, 2, 3, I end up there. Do I have any overlap? No overlap, so that's going to be a great one there. The next one, 13 and 10, if I just add 3 to that, I'm at 13, I've already overlapped that one, so it's overlap, so no. And then 7 and 15, same idea. We have 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so it's even further away to start from. We go up 3 here. We can go down 3 there. Do we have any overlap happening? No, so that's going to work as well. Number 2. These two box plots show distances of a standing jump in inches for a random sample of 10-year-olds and a random sample of 15-year-olds. So here's our box plots here. We have, in this case here, we have a median value of 56, and median over here of maybe about 69. Okay, so 69 is the median there, 56 is the median there. Okay, so that's good information to have. Is there a meaningful difference between in median distance in these two populations? So what is the difference of medians? In this case here, we would do 69 minus 56, so our difference in medians is 13. Now, remember we talked about doing like express the difference in medians as a multiple, blah, 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 that whole thing? Okay, so we had 13 was going to be equal to, now for this number here, we need to multiply, in this case here, by our make it equal to our IQR. So what is our IQR? Remember the IQR is quartile 3 minus quartile 1, and we want to use our larger IQR value. So this IQR we have over here, we have 70s, Q3 is at 70, this is Q3, and quartile 1 is over here at 65. So 70 minus 65, the IQR for this is what? 70 minus 65 is 5. The IQR here for quartile 3 is at 58. Quartile 1 is at 53. So 58 minus 53 is also 5. So my IQR for both happens to be 5. So we're going to do 13 equals 5 times a value we don't know. So we got to find that value real quick. So let's do 13. So to find that value, what do we do? Well, we'll do 13 divided by 5 to end up with 2.6. So the question is, like always, is 2.6 is greater than 2, and 2 tells me that there is a significant difference, right? Or a meaningful difference, I should say. Anything greater than 2 is a meaningful difference. Okay? So because it's greater than 2, 2.6, we're going to say it has a meaningful difference there. All right? So hopefully I explained that clearly enough for how to get those values there, where the larger IQRs, there wasn't a larger one this one, they were the same, so it worked out fine. But that's how we get a number of 2.6, and we can prove that because that the difference in the median distance is greater than 2, then it has a meaningful difference there. All right, let's look up the next one. All right, the median income for sample people from Chicago is about $60,000, and so Chicago median is $60,000. The median income for sample people from Kansas City is $46,000. But researchers have determined that there is not a meaningful difference in medians. Explain why the researchers might be correct. Okay, so think of it like this. Let's think of some values here. All right, let's go ahead and put down 46,000, right, 46K, and I could put down 60,000 over here. Now the difference between the two medians, the difference here, is going to be 60 minus 46. So you're only talking about a difference of what, $14,000 is the difference there. Okay, so most likely, if they're saying there's not a meaningful difference, that means that there's some overlaps in the data, right? So if they were doing a median, you might have a box and whisker plot that had some values here and here, but this one extends out to there, and that one extends here. This one might have a box and whisker plot, looks something like this, but extends here to here. So because it would have some overlap, you would say it's not significant or not meaningful difference there. So, yeah, so that's what it is. So the medians differ by 14,000. So if the IQR, the inner quartile range, would have to be greater than 7,000 in order to make a difference, because 7,000 going this direction has to overlap some way, right? So the IQR would have to be greater than 7,000 this way to show no overlap, to show, it does show. Yeah, so there's going to be overlap. So, anyways, too much overlap. That's the big thing. A farmer grows 5,000 pumpkins each year. The pumpkins are priced according to their weight. So the farmer would like to estimate the mean weight of the pumpkins he grew this year. He randomly selects 8 pumpkins and weighs them. Here are the weights in pounds: 2.9, 6.8, 7.3, up to 15. Wow, so a big difference from 2.9 to 15.3. Big difference. Estimate the mean weight of the pumpkins the farmer grew. So if I'm looking at all this, I'm estimating all that, I would estimate that to be somewhere in the middle of this group of things, which is going to be putting it right about here. So I might estimate between 7.7 and 8.9, so maybe about 8.5 pounds. Again, just an estimate. This dot plot shows the mean weight of 100 samples of 8 pumpkins, similar to the one above. Okay, so my 8.5 would be somewhere about here, right? There's my 8.5. What appears to be the mean weight of the 5,000 pumpkins? Well, the 5,000 pumpkins are pretty spread out. So when I look at where that curve kind of starts to bend over a little bit, we might be somewhere about here. Okay, so the mean there might be somewhere about maybe 10 pounds, so between 10 and 10.5 pounds, somewhere in that region is where the mean weight looks to be, like, somewhere in there. So what does a dot plot of sample mean suggests about how accurate an estimate based on single sample 8 might be. Okay, it would tell me that the sample I used was not too good. It's not very good, right? I got 8.5, and this is off by about 2 pounds. So not a very good sample there. So what might the farmer do to get a more accurate estimate? He should use a larger sample size and maybe do it multiple times to get a feel for it. All right, that's it for today. Sorry for that length. Hope you have a good day. We'll see you next time.